So the question is, why are we here? To run our calculations on the compute cluster. And as we will see, the compute cluster is different hardware than you're used to on in your notebook or under your desktop with your desktop computer. But the idea is to use all of this hardware using parallelization. So what's the main idea? The main goal is to reduce calculation time. So we have some kind of sequential calculation, read some input, then we do our calculation steps, and then we write our result. And the idea is now that if these calculation steps can be calculated independently, then we can do this in parallel. Therefore, our parallelized version looks like this. We read some input, then we have to distribute this input data and run the calculation, these steps in parallel. And then we have to gather the results and write the results down in a result file. And then we are done. And because these calculation steps are done in parallel, we save some time and our whole calculation time is reduced in comparison to the sequential version. Now, the question is, when we split up these independent parts of our calculation and run them in parallel, how do we split them up? How does this communication work? And how do we run these parts on actual, real physical hardware? So if we have multiple cores, or do we have multiple CPU sockets? Do we have multiple compute nodes? And so on. And for this, we have to know about our hardware. What hardware do we have? And what's the best way to parallelize our calculation? And this is why we're going to take a look at the hardware on the real cluster. And we will start basically from the most coarse-grained view of the cluster when we are standing in front of it, down to the very smallest parts of it. So if we stand in front, so here we have two pictures from the front side and from the, actually it's the side view. And it's a cluster by Lenovo with 13 water-cooled racks and 6 air-cooled racks. And we see here these rows of racks here. And this is how it looks like when you visit us in our white space. And as we can also see, the racks are connected on the bottom of the racks through the floor, but also on the top. So from the top there comes the power. We have these red boxes where the power from the facility is distributed to the racks. And we also have these yellow canals, you could say, where the racks are connected with each other, where the networking cables are basically inside. And for the cooling, the racks are connected on the bottom on this second floor below this normal floor. So you see there are tiles that can be removed on the floor of the white space. So here we see on the left side a schematic of the racks from the top. So it's basically a floor plan, and we see the racks here. And on the left side, we see the cooling distribution unit. Let's start with the racks. In this design of the cluster system, we have a certain main unit. So these are compute pods, they are called by the manufacturer. And the idea is to have two computer racks combined with one management rack. And we see this here if we have these three racks. So this is a picture during the assembly of the cluster. We have the two outer racks where the compute units are inside, and then the middle rack where networking hardware and some administration nodes and so on end up. So we have 5 of these 3 rack groups, and then we have 4 more racks here on the side. And we also see that most of these racks are filled with compute units that have CPU only compute hardware, but we also have these racks where there are GPUs inside, and we also have some racks where we can add PCI Express acceleration cards inside, and these will be used for FPGAs. So another type of accelerator cards. And this cooling distribution unit is now used to cool the racks. So as we've seen, the power comes from the top. It goes in through the compute units, and all the compute racks are connected to this piping under the floor, and therefore the liquid water cooling, the liquid goes through these pipes, is connected to the racks, goes through the compute units where it is heated by the computational hardware, by the GPUs and CPUs. And then the hot water flows back through the pipes into the cooling distribution unit. And here are basically the pumps that are pumping the liquid through this loop and connected to this heat exchanger that connects this cooling distribution unit to the cooling loop of the facility, of the building. And these pipes are below the floor. And this way, the power goes inside of the racks, it gets heated up, and then it gets transported and exchanged to a different cooling liquid loop, and then transported to the top of the building, where it is then exchanged into the environment, or it is also used to heat the buildings in the near vicinity of our compute center here, to use the heat productively. So as we've seen here, we have in total over 600 compute nodes, and in each node there are two AMD Turin CPUs, and we have some memory. There are also these compute units with even more memory, and then we have the GPU nodes and the nodes that can also host some acceleration cards. And for the networking, we are using, for the low latency, high bandwidth networking, InfiniBand switches, but we also have Ethernet switches for management networking, and everything is also connected to the storage that is then hosted also in these management racks. Next step is we're going to take a closer look at one of the compute blades. So a blade is basically like a flat box that is put inside of the racks. So there are many blades in a rack. And in this cluster in Otos, we have two compute nodes per blade. So one compute node is basically like one computer, logically seen, and it is connected then to the power, the cooling, and the network. And as we see here, one of the nodes consists of the two CPU sockets, then the main memory that is here next to the CPUs. Then we have the main board below, and in the back we have the network interfaces, and here also the water cooling pipes that lead the liquid through past the liquid past the memory and the CPUs. Now, if you take a closer look to one of the nodes, so basically, for example, the left one here, and look at it logically, then we see it's a complete compute machine, which consists of two CPU sockets. and they are all accessible by your programs that run on the compute node. So all the processes that run on one of the CPU sockets can access the resources that are connected to the other CPU socket. Therefore, we are calling this a symmetrical multiprocessing system, because every program can access all of the resources. And we see that a CPU socket has its memory interface to connect to its part of the memory, and then the connection to the other CPU socket to exchange some data, for example, between programs that run on both of the sockets, or to access the memory of the other socket, or if some of the networking or accelerator cards are connected to one of the CPU sockets, then also the other CPU socket can reach these peripherals here. Let's take a closer look at the memory, because this is quite important for computations. As we've seen, we have the two CPU sockets, and each CPU socket has 12 channels to memory, and behind each channel can be one or more DIMMs, therefore a memory, little memory card that you can slide inside on the main board, as we see here. So there are 12 per socket, 12 channels, and it's we are using DDR5 6400 as a memory communication standard here. So we have 32 gigabytes per DIMM, and this makes a total of 384 gigabytes per socket, and a total of 768 gigabytes per node on a normal node on autos. So in this picture we see basically the main board. If you remove all of the heat spreader, the metal to transport the heat to the liquid to exchange it, and we see here the empty memory slots, but we see the CPUs inside of their sockets, and there is these heat exchange pads. This paste is still on them. So this was a picture during maintenance, where it has to be disassembled, repaired, and assembled again. So as a side note, if you have any questions, you can always interrupt me or speak up on the microphone. That's no problem. The same what? It is very similar, but there are other CPU. So it's the question was if the setup is the same as in Noctua 2. So we have different CPUs on Noctua 2. They are AMD Zen 3 CPUs, but they are also basically server grade CPUs. And as we will see on Autos, we have 96 cores per CPU, and on Noctua 2 we have 64 cores. And we have also the CPUs on Noctua 2 have less memory channels, and also a little bit less of main memory than on Autos. But conceptually, it's very similar. There are also two CPUs per node. But as we will see, the CPUs themselves, there are still many differences. Now, memory bandwidth is quite important for your calculations. So you want to calculate something, do some calculations, but you first need to get the data inside of the CPU, and then you need to get the results back into the main memory. Therefore, this memory transfer is quite important for a good performance. And if we look at the theoretical maximum bandwidth of the memory, then we will see that we can compute a peak bandwidth of over 600 gigabytes per second. But if we actually measure it, then it's a little bit less. There's some overhead, maybe some congestion um, going on, and we can reach maybe 540 gigabytes per second if a process runs on one socket and accesses the data in the memory that is directly connected to the socket. However, if the same process accesses some memory on the other sockets, so the data has to flow through this socket interconnect, and this becomes a bottleneck. So if we measure it, we can maybe get 180 gigabytes per second unidirectionally through. So I've explained we have a system where every process can access all of the resources. However, not with the same performance. As we see here, there's a performance difference in if we access the directly connected memory or if we access the other memory. And this kind of system we call a non-uniform memory access system, a NUMA system. And this means that the performance is not non-uniform depending on what kind of memory you are accessing. And at the same time, still the coherency of the data, for example, if one process is doing something with data that's in its on the one socket in its main memory, and then the other process is accessing it, then there's still coherency in the logic of your program uphold. So the CPUs also have cache, so this becomes complicated, but the CPU basically has certain guarantees that the caches in the CPUs have coherent data. Now, one of the consequences of this kind of system design is that local memory accesses are more performant than the remote memory accesses, and this is one thing that one can keep in mind on these larger systems. So this usually does not happen on, for example, notebook CPUs where you have also not as many memory channels. We can take a little closer look at how these CPUs are constructed. So we already seen that we have some kind of hierarchy in the architecture. We have the racks, we have the multiple CPU nodes per rack, and then we have two CPUs per node. But as we see here, also inside of one CPU socket, there's still a hierarchy. And this picture is from a different model than in Otos. It's an AMD Rome CPU, but the idea is the same. That on the CPU itself, on the package, we actually have multiple chips. So this makes the manufacturing of the chips easier, and because the size of the chips is smaller, so the probability that you have a working chip at the end of the chip production is higher, so the yield is better. But you can combine these chips on one CPU package and connect them and make a complete CPU out of it. So in the middle we have the I/O die. This I/O die is connected to the memory and to the other socket and the peripherals, for example, the networking card, and also the memory interfaces are on the I/O die themselves. And we have these smaller dies. These are the core dies, they hold the actual CPU cores that do the calculation and also the cache of the CPU. So this kind of design is called a chiplet design. We have multiple dies, they are packaged onto one chip, and this allows also for modularization for multiple different models of CPUs. You could get a large chip as we have with 12 CCDs on one CPU, or if you don't need as many cores on one CPU, you can also get a model with less CCDs, which would also be cheaper if you don't need this kind of computational power. So here we have our 12 CCDs that are connected to the I/O die, and the I/O die is then connected to the other socket and then also to the memory and the over the PCI Express lanes to the acceleration cards or networking. So we see here in the middle the L3 cache, which is shared by all of the cores, and the L2 and L1 cache that is then private to the CPU cores. Now, inside of the operating system, there is a certain grouping of these CPU cores, and these are called NUMA domains. And a NUMA node does not mean a compute node, but a NUMA node is one of the groups inside of the operating system. So one NUMA domain. And in Otus, we have configured the system to have 2 NUMA domains, one per CPU socket. And the operating system uses this information to decide where allocated memory should be placed in physical memory. And it has a certain values for the access of the memory from a certain CPU core. So if you access memory inside of your NUMA domain, so this is this local memory access, for example, from one of the CPU cores in this NUMA node, then you would have a modeled performance of 10. If you access the memory on the different NUMA node, which is on the different socket, then it's 32. This should model this performance difference in memory access and should help the operating system to decide where the data should be placed. Note here that the Otus login nodes have only one socket. So if you look at the CPU cores and so on, you will see the same number of logical CPU cores, because on the login nodes SMT is enabled, simultaneous multithreading, but actually there's only one physical core on the login nodes. So this thing is true for the compute nodes, where also your calculation will be take place. Now, what to do of this as a application programmer, as a developer? So what the question is, how are the memory pages? The data is actually distributed by default, and there's a certain golden rule of CC_NUMA, and it means a memory page gets mapped into local memory of the processor that first touches it or writes to it. And if you think in the logic of an application, you are allocating some memory, you're initializing it, and in case of application with multiple threads that are running on multiple cores, then they all have to access this data in the memory. Now, if the main thread allocates and initializes this large array, and then all of the worker threads are accessing it, then some of the worker threads will be in the same NUMA domain as the main thread, but some will be in different NUMA domains. And now if all of these threads are accessing the this array, this will be there will be a slowdown, because then they have to go through this bottleneck, and because the data is the position of the data is decided when the array is initialized. So allocation only means like a note to the operating system that I'm gonna need this memory in a moment. And initialization means that I'm then writing it, for example, to zero it out to prepare it for calculations. And when the first reading or writing to a memory page happens, then the operating system will decide that it will go to a certain place. And because the main thread is initializing the complete array, it will go, for example, in only this memory region here. And the alternative is, because of this behavior of the operating system, as an application developer, you should, if you parallelize the calculation and all of the threads are only accessing one part of the array, you can let also these worker threads initialize their part of the array. This way, only their part of the array is then actually physically stored in their local part of the complete memory, and therefore their local access to this part of the memory will be way faster. Now, if you are on site on a compute cluster node or on any compute cluster node, there is a command to figure out how many cores do you have and what are the NUMA domains or the NUMA nodes. And it is NUMA CTL minus capital H, and you will get a large output. So here we have in total 192 CPU cores. And as you see here, we have two NUMA nodes, node 0 and node 1. And you also get the size of the memory that is logically grouped into this NUMA node. And you also get this little matrix here that basically has, if my process or thread runs on one NUMA node, then the local access is fast with the 10 and the other access is slow with the 32. Now I've talked about Otus, and now we're gonna see the same output, but for Noctua 2. And the difference is that on Otus we have 2 NUMA nodes, and on Noctua 2 we have 8 NUMA nodes. So the principle is the same, but the grouping is a little bit different. And therefore also this output is different. So we see we have 128 cores, and then they are grouped differently here. And we have another hierarchy level here because the access in the same NUMA node is with 10, has again this modeled value of 10. To a different NUMA node on the same socket, it's a 12. And if you pass this socket barrier, you have to go through the socket interconnect, then it becomes a 32. And the reason for these configurations is that you can get a higher performance by using this configuration. If the memory is, as explained, stored locally and the accesses are only locally, then you get a higher total performance out of the memory than if you would configure it differently. On Otus, we did some measurements and we decided that there's only a difference of a few percent of performance difference in real applications, or in a few percent in the measured bandwidth on some benchmarks, and in real applications not a real measurable difference, and therefore it's this easier configuration of only 2 NUMA nodes. But if you're Noctua 2, then it will look like this. And you can also use NUMA CTL for some configurations of your program for benchmarks. So if you, as we will see in the hands-on, you can use NumaCTL to decide where the memory should be stored by the operating system if you run your program with this command. So you have to tell with membind which NUMA node to use to store the data. And you can also decide on which NUMA node the threads are allowed to be executed. And this way you can do a benchmark and say my program runs on one NUMA node, but the data is stored on a different one, and then you will see a certain difference in the performance or not, depending on the program that you're running. Now, the reason why we are spending so much time on the memory is because it is basically a bottleneck in your, or can become a bottleneck in your computations. Many computations are memory bound, and this means that they depend on a good performance of the memory access. Because the CPU cores, as we see here in the model where we have the CPU cores on the top, if they do some memory accesses, some memory requests, it has to go through the chip. In this system, it has to go out of the CCD into the I/O die and out of there through the memory interface into the memory. Therefore, it has to even go out of the chip to go to the memory and then back again through the memory interface and so on. Therefore, there's a long way for the data to reach the CPU core where you actually are doing the calculations. So there's a certain gap of the computational power and the performance of the memory access. And this is also the reason why in between the core and the memory there is a cache hierarchy that caches your data when you're doing memory accesses. And as we see here, we have on this system level 1 and level 2 caches that are private to the core, and we have the L3 cache that is shared by multiple cores. To be precise, by the cores on the same CCD on the system. We can take a closer look at the cache, and we can start from the top with the L1 cache. We have 32 kilobyte per core of instruction cache and 48 kilobyte per core of data cache. And here the access latency from my calculation is running. I need to get some new data. I'm accessing it. It's inside of the level 1 cache, and I get it back after 4 cycles. And the level 2 cache is also belongs to the core. It is larger with 1024 kilobytes per core. And here we already have a larger latency of 7 to 18 cycles only to get the data out of the cache back into the core. And in this time, basically, the CPU waits for the data. And then we also have the L3 cache, which is even larger and even has a larger latency. So we see there's a certain trade-off. We have this very fast cache, but it's quite small and it's next to the core, and we have the larger caches that are further away from the core. And as we also see here in this CPU architecture, we have the L3 cache is a so-called victim cache. And this means, for example, your program starts, it accesses some memory. The memory is not inside of the caches, and it is received from the main memory and then stored in the L2 and L1 cache. And now if your program runs and fills up the caches will get full, and then to actually store the new data, the old data has to be removed from the cache and it is then removed from the L2 cache, but because it was a victim of this removal process, it gets stored in the L3 cache. And now, if you get the need the data again and request the data, it can be fetched from the L3 cache if it's still inside of the L3 cache. And this L3 cache is then shared by multiple cores. And we see here it's 4 MB per core. Now there are some more architectural features that I just want to mention and not go into much detail. We have simultaneous multi-threading, which means that one core can execute instructions from multiple threads at the same time, but this is disabled on Noctua and Otus because this often helps with less optimized programs or daemon programs that run in the background of your operating system. And this helps with saving energy, for example, on notebooks, but on HPC systems where you have very optimized applications, this only adds contention between the threads of your application, because the single threads already are good at using the resources of the CPU core. Then we have pipelining, and pipelining means that the execution of the instructions and also the steps inside of your CPU pipeline, they are split up into multiple steps, and therefore more instructions can be executed at the same time inside of these execution units, and this basically improves the performance of executed instructions inside of the CPU. And this is built inside of the CPU architecture, and you basically can't turn it off. It's just optimization inside of how the CPU is built. Then we have super scalarity, and this means that the CPU can run multiple instructions at the same time, not even of the same type, for example, only floating point multiplications, but it can even decide that instructions that are independent of each other can be executed at the same time, or even overtake each other and be executed in a different order than they are in the actual program, than they would be executed by if you would execute one instruction after another. So the CPU can look ahead and see, okay, there are more instructions that can already execute because I have the resources for that, and and I don't have to wait. And then we have a very important optimization, which is a single instruction, multiple data. And this is something that you have to enable in the compiler to be used. So the compiler has to know that it's allowed to use this optimization, and this means that you can execute instructions on multiple data values. So you put multiple values in a vector, and then do the same instruction on multiple values in the vector. For example, you're loading 8 values in the first vector from your memory and 8 other values in a different vector, and then you can do, say, add them element-wise, and then you get a result vector of 8 values in your result vector. And this immensely improves the performance, because then all these 8 operations are being executed at the same time if the CPU architecture supports it. For this, you need to have more resources, more execution units inside of the CPU, and also the memory access needs to support this um, to feed the CPU with enough data, so it can actually perform all of these calculations. Else you would have the resources inside the CPU, but would wait for data until it arrives, and then you have basically unused resources. So the complete CPU has to be adapted and enlarged with resources to um, have an actual performance increase. But as a developer or user that has to compile the software, you have to enable it in the compiler so the compiler knows it's available in the CPU and I can make use of this. Now, as you already see here on the left side, we are going through the hardware architecture or hardware hierarchy of compute cluster from the top to the bottom, and we ended up at CPU cores, and this is basically the last point, which is it's not smaller than CPU cores, but it's basically an addition, which are accelerators that you can use to accelerate your calculations. Very well-known GPUs. So these are many-core multiprocessor um, hardware. For example, the NVIDIA A100 in the Noctua 2. We have the NVIDIA H100 in Otus. And here we have a different architecture, as you already see at the picture. We have thousands of very small cores that can do um, many independent computations in parallel on many data elements. And we also have FPGAs. So these are a specialty of our compute center here, where we use and research these type of accelerators. See, these are field programmable gate arrays. And this basically means that on these chips, you have a grid of these computing resources, and you program all of these small compute blocks, and then you connect them and decide how the data flows through these compute blocks. And this way you can have a very customized compute logic and where the data flows through your custom design, and you do all of these special computations that you need. We've seen many levels of hierarchy, and they are. It's important to understand this hierarchy to make the best use of the available hardware. And as an application developer, this means you have to design your program to make use of all of these features. So you have to look at the memory accesses. You have to enable and make your program to be fit for the compiler to use SIMD instructions, and look at what happens if can I parallelize the computations on multiple threads and so on. And as an application user, you have to properly compile the program, for example, to use these SIMD instructions. And you have to properly pin the processes and threads to cores. As we will see in the next section, how to do this to make the best use of the hardware to not create some bottlenecks that can be avoided. Let's go quickly through the hierarchy as we've seen it. We begin with the racks, and all of the racks are then connected via the networking. And inside of the racks, we have the blades, and in this case, we have two nodes per blade, and then we have one node. On each node, we have two sockets, and then we have on one CPU socket, on one CPU, we have 12 of these CCDs, and per CCD, we have 8 cores down to our CPU cores. Now the question is, in all of or many of these levels, we can make use of the parallel computation, calculations, and down at the bottom level we have the data parallelism with SIMD instructions, and this you can use via your compiler. We have the architectural features at the instruction level that are built in inside the CPU. Then we have the thread level with multiple cores, so you can parallelize your program to split your calculation into multiple cores. And this also depends on support of the compiler or your language, because then you need to think about how these threads exchange the data, the information over on one compute node. And then up to the process level, you can run multiple processes on one node. But then you can also run multiple processes on different nodes, and then you have to think about communication over the network. And for this on HPC, traditionally, you can use MPI, the message passing interface, to make your processes that are running on multiple nodes communicate to exchange information